Next, we're going to be talking a little bit about liquids, but even when we're talking about the liquid state of matter, we're going to be talking about properties that relate to gas and the conversion between liquid and gas. So compared to gases, liquids have less motion of particles, as you can see by this little video here, and the particles are also closer together. So remember with the kinetic molecular theory, they said that the volume of space between particles and gases is much larger than the actual particles themselves. In liquids, that's not the case. There's not that much space between particles. They're free to move around, they interact with one another a lot more, so they are bound by attractive, what we call intermolecular forces, that gases do not experience. So real gases do kind of experience these intermolecular forces, but ideal gases, of course, do not. So intermolecular forces, inter means between. So we're talking about forces between molecules. Intramolecular forces are basically like chemical bonds, specifically covalent bonds of molecules. So here I have a diagram. It's a glass of water with, where are we? There we go. Some water molecules here. There are intermolecular forces, IMFs, that are depicted by red lines between molecules. We will be talking about different types of intermolecular forces, one of which is hydrogen bonding, which is very prevalent in water molecules. And it gets confusing because we say hydrogen bonding, but it's not a bond within a molecule. It's an intermolecular force between molecules. So basically the hydrogen, those little ears on the water molecule, are attracted to the oxygen in another molecule, as well as the oxygen within that same molecule. So there are little blue lines between the hydrogen and oxygen of one molecule. Those are the covalent bonds that we see. And there are also red lines between two different molecules. Those are the intermolecular forces. Different substances do have different intermolecular forces and different strengths of intermolecular forces, which is going to affect a lot of the properties of that liquid. So especially boiling point and vapor pressure, which we will talk a little bit about today. So surface tension is a quality of some liquids experience, but not all do. One that does, that's really important, is water. So surface tension is why those little water ski bugs can float on the top of water, or why you can float a paperclip on top of water, even though you can easily drop a paperclip in water and it will sink. So in a sample of liquid, there are particles that are on the surface of the liquid that do not have any attractive forces from other liquid particles above it. So within the middle of a liquid, those particles have attractive forces all around them. But at the very, very surface, there are only intermolecular forces below and to the sides of that particle. This creates a tension on the surface of the water that basically acts like a film that's stretched over the water. So the stronger intermolecular forces you have in a liquid, the higher surface tension you will have. If you don't have very strong intermolecular forces, you're not going to have a high surface tension, and you're not going to be able to float things on that liquid. This is also what allows water to form beads. So like when it's raining outside and you see beads of water streaming down your window, that's due to the high surface tension of water. There are, of course, evaporation and condensation, which is a transfer from different states of matter. So vaporization is when a liquid becomes a gas. In order for a liquid to become a gas, it has to basically overcome the strength of intermolecular forces that's in the liquid phase. So heating a liquid is going to increase the number of molecules with enough energy to escape. Evaporation is the conversion of liquid to gas below a liquid's boiling point. And condensation is basically the opposite, when a gas becomes a liquid. So in a sitting glass of water, there are some particles that do have enough energy to escape into the gas phase. So when you have water sitting on your desk, there are some water particles that are evaporating into the atmosphere. In a closed container, we can basically trap most of those particles, and then they condense back into the liquid phase, and when the evaporation and condensation of the liquid are equal to one another, you have something called dynamic equilibrium. So remember the energy kind of curve, the average kinetic energy that we talked about in the last video? You do always, most likely, have some particles that can evaporate. They can escape into the gas phase. If you were to increase the temperature, then you increase the number of particles that have that energy. So the higher temperature of a liquid, of water, the more particles you will have that can evaporate. So that's what this diagram here is showing. It's like if you have a cold glass of water versus a hotter glass of water, the number of particles that you have that can escape are that area under that curve, so it's higher for the higher temperature glass of water. There's also something called vapor pressure, which is the pressure of those evaporating liquid going to gas molecules, the pressure that they exert above the surface of that liquid. So it's directly related to the strength of intermolecular forces. So if you have like water, if you have something with strong intermolecular forces, it's going to have a relatively low vapor pressure because you don't have that many molecules escaping into the gas phase. If you have a substance with weak intermolecular forces, they have a higher vapor pressure. And one example of this would be anything that's an alcohol. So ladies, if you've ever removed nail polish, or gentlemen, I'm sure you have sisters and mothers that have painted their nails, you will notice when they remove nail polish, you can smell it, okay? The reason you can smell that nail polish remover is because it's an alcohol. It has weak intermolecular forces, so they have a high vapor pressure. There's a lot of those molecules that are escaping into the air, which then you can smell. So vapor pressure will also increase as temperature increases. Same reason that evaporation is going to increase. When you increase the temperature, you have more particles that are able to escape because they have higher kinetic energies. When your vapor pressure, the pressure exerted by gases from that liquid, equals the atmospheric pressure, the pressure of the atmosphere on the surface of that liquid, once those are equal to one another, you have boiling. Okay, so you might notice whenever you're making pasta or something, there's instructions that say, like, at high altitudes, this is how you cook it. So there are different boiling points of water depending on your altitude. So molecules throughout the liquid, when boiling occurs, they have enough energy to vaporize, which is why you have those bubbles forming in boiling water. Those bubbles are actually water molecules in the gas phase. That's what creates those bubbles. And finally, we have a vapor pressure curve. So you may see this. It basically compares the vapor pressure versus the temperature of a liquid. And you might have different liquids on there. So here, the yellow curve, we have water. Has a relatively high boiling point. So this is at 1 atmosphere, which is 760 millimeters of mercury. That would be the boiling point of water, 100 degrees Celsius. That's relatively high compared to other liquids. So ethyl alcohol, like I said, alcohols have a relatively high vapor pressure compared to water, and ethers are kind of the same. They have a very high vapor pressure. So that means these two have weaker intermolecular forces compared to water. So if we look at a given temperature, 60 degrees Celsius, the vapor pressure of water is about maybe 100 millimeters of mercury, whereas the vapor pressure of ethyl alcohol is about 400 millimeters of mercury. So you can kind of compare at a given temperature what the vapor pressure of different liquids are, and you can see how their boiling points differ. So water, again, has a boiling point of 100 degrees Celsius. Diethyl ether only has a boiling point of about 30 degrees Celsius. Okay, so that is pretty much liquids in a nutshell, properties of liquids. Let me know if you have any questions.